In this video, we'll take a look at some basic applications and definitions of drive and check surfaces and containment boundaries. Now, a surface can be either a two-dimensional or three-dimensional entity type generated from curves and used to describe the skin or interior features of a part. Now, this pink surface back here would be an example of a two-dimensional surface. It's basically a flat plane. And this green wireframe geometry, which is composed of three lines and a spline at the base here, constitutes the boundary of that surface. If I turn my shading to translucent, you can see the wireframe outline of that surface. On the other hand, this orange surface here is a three-dimensional surface, and it is generated from these two lines here and two connecting splines. It's important to note that surfaces have zero thickness, but they do have normals. A normal is a vector perpendicular to the tangent plane of the surface, and is usually the face that you are working or machining on. I'm going to change my translucency back to fully shaded, and then hit Alt-S and completely unshade this model. Now you note that this unshaded grid that's displayed on my surfaces is the color of the entity. That signifies that the normal is facing in this direction. If I were to rotate this part around from the underside, you will see that now the grid is gray in color. This signifies that the normal is facing the other direction. So if I go back to my top view here, and then I can go to Edit, Set Normals. I'm going to select this surface here, click OK, and we can see the arrow indicating the direction of our normal, which is indeed perpendicular to the face of this planar surface. I'm going to leave my normals how they are right now, because they are set in the proper direction for machining on the top of this model. To utilize the surface toolpath, I need to select a drive surface, and that will be the surface where machining will take place. Here I have a simple surface finish parallel toolpath. For my drive surface, I've selected this orange surface here. If I click Show, it's highlighted and displays that is the surface where machining will take place. I also have the ability to select check surfaces. I don't have to select a check surface, but I have the option to. Depending on your license level of Mastercam, it determines how many surfaces you can select for drive. A Level 3 sim will allow you to select any number of drive surfaces. A Level 2 sim will only allow you to select one drive surface per toolpath. However, for check surfaces, both Level 2 and 3 allow unlimited check surface selection. Let's take a look at a back plot now of this simple toolpath with that drive surface. And there's our one drive surface being machined pretty much as expected. However, upon closer examination of the intersection between these two surfaces, we can see that the tool would be colliding right through this planar surface here. Let's run that again from this view and take a closer look. And we can see very easily there that the tool is driving right through this surface. So what this toolpath needs is a check surface, which by definition is a surface that will not be machined. So I need to go back into my geometry selection here and add check surface. I'm going to select this pink surface, OK, OK, and then regenerate. And then we'll backplot that. And now Mastercam is avoiding that check surface. As it is now, Mastercam is machining right up to that check surface. It's important to note that we have the ability to enter how close we come to that check surface and also how close we come to our finished drive surface. Let's go into the parameters here and take a look at entering some values. So we enter the operations parameters, surface parameters, And here we have stock to leave on drive and stock to leave on check surfaces. Now all surface toolpaths will have these options. So if I'd like it to stay away from my planar check surface that I have selected, we'll set an unrealistic amount so we can see, for an example, 1/2 inch, and then regenerate and backplot it. We'll see the tool is now ensuring that there's going to be 1/2 inch of material left on this check surface here. We'll go back into the parameters and set that back to 0, and then click OK and regenerate one more time. Now containment boundaries also have various applications in surface machining. I'm going to go into my levels manager and turn on level 2, on which I have a containment boundary drawn. Now a containment boundary is one or more closed set of curves that will limit the tool motion. It doesn't matter where the containment boundary is, whether it's on the surface of the part or above it at any Z level. Here I have it floating above my part. I'd like this tool path just to machine inside of this deeper V section here. So I'm going to go into my geometry and then add containment boundary here. I'm going to select chain, and then regenerate. And then we'll backplot. We can see that tool now is driving on that surface, checking against this pink surface, and staying within this containment boundary. Let's switch to top view and take a little bit closer look at the containment boundary. You'll notice that the tool center line is actually contained within the boundary. It's almost analogous to having cutter compensation turned off in 2D toolpaths. What if, however, I wanted the entire tool to stay inside of the containment boundary? Then I would go into my parameters once more, and here I have tool containment. I have the option to compensate to the inside of the containment boundary, the center, which is where we're set now, or the outside. If I click inside and then regenerate this tool path, and let's backplot it, looking at it from a top view. Now we can see that tool is entirely staying within the containment boundary. The last option here on containment boundary is outside. Let's take a quick look at what that does by regenerating and backplotting one more time. And we can see that the tool is actually allowed to go entirely outside the containment boundary, as long as it just machines our drive surface and stays off of our check surface still, of course. Now our example here was composed entirely of surfaces. If your model is a solid model, or if you prefer to work in solids, the machining is identical, as is the surface selection and the function of drive, check, and containment boundaries.